let's look at this short session on the topic elasticity. So here I would say this topic also is no less than free marks, because the moment you get any question from this topic, you should try reading it, try understanding it, because topics like rotation and like they have so many concepts, right? So many concepts that you have to understand, and you can get a question from any of the concepts, right? So it takes a lot of time to master a chapter like that. But a chapter like this, there are very few fundamental concepts. Using these fundamental concepts only, they are applying in different problems. You're supposed to just solve 5 to 6 models, right? 5 to 6 different models and get a feel of what elasticity is. And after that, I'm sure you can do any question based on elasticity. So let's quickly revise and let's quickly look through what all we have to study. So we'll first see what elasticity is, then followed by understanding properly what is the definition of stress and strain for 3 different cases, right? Then we'll look at the stress strain curve. Yeah, from that we'll actually understand what Hooke's law is, and then we look into the 3 moduli of elasticity. And then there is our part called Poisson's ratio, which is a very small topic, so we'll quickly look into that. And then we'll understand finally that okay, if I have a wire and if I stretch it from both sides, right, and if I remove these 2 forces, it will come back to its position, right? But in the meanwhile, if I keep a mosquito or an insect or an insect on this, and if I bring it like this, the insect might gain some kinetic energy from this and might fly off, right? It can happen. It is just a vague way to understand that when I stretched it, there was some energy that was stored in this wire, right? On that energy was transferred to the insect, which gained the kinetic energy when it was sitting on the wire before it came back to its actual position. So let's quickly look into these topics. So let's look into understanding first what is elasticity. So I will explain you the tendency of a body to resist the change in shape is called elasticity, right? So if I put some force on the body, like if I take a body, if I pull it from both sides, if it easily changes its shape, right? If I remove it, if it comes back to its original shape easily, right? Or you could say if it has a greater tendency to resist the change in shape, then I will say that the body is more elastic, right? So it's a misconception. If I ask you which is more elastic, rubber or steel, you would tell me that rubber is more elastic than steel, because we've been using this term a lot, more and more, right? Rubber is very elastic, steel is not elastic, right? We've been using this term more and more, but steel is actually more elastic according to physics. According to what we study here, physics, steel is more elastic. Why? Because when you put some forces on the steel, it comes back to its original shape easily. In fact, it doesn't even allow you to change its shape that easily, right? Compared to rubber, if you put some high force on rubber, and if you remove those forces, it's not necessary that the rubber will come back to its perfect original shape, but the steel definitely will, right? Steel has a greater tendency to resist the change in shape. That's why I will say steel is more elastic than rubber. I hope you have understood what elasticity is. Now we'll look into understanding what stress is first of all, and then followed by strain. So stress is simply given by this formula: restoring force by area. So what happens is, there are 3 kinds of stresses. We'll look into the first stress. First of all, vaguely understand what this is. You apply some force on the body will apply an equal and opposite force on you, like to resist, right? There will be some force which will bring the body back. So if I pull the steel or rubber on both sides, if I remove it, there are some internal forces which will actually bring it back to shape. They are called restoring forces. They are having the same magnitude as to what force you applied, right? So that force by the cross-sectional area of the material is called stress, right? So we'll look at 3 kinds of stresses. First is your longitudinal stress. Longitudinal stress. So longitudinal stress is very simple. If you have something like a rod, like a straight rod, right? If I apply some force on both sides, and the cross-sectional area is A, right? Very simple, don't get confused. It is simply F by A, because they're applying a normal force on both sides. That F by A is called the longitudinal stress, because this will produce a longitudinal strain. Longitudinal means along the line. It will produce a strain, a change in length along the line. That's why it's called longitudinal strain. Coming to the next one, we have what is known as a shearing stress or a tangential stress. What do you mean by shearing stress? If I have a cube like this, if I apply some force on this side, right, either from both sides or if it's so rough, if it's so rough that it's just kept on the surface, you apply some force, the friction itself will oppose your force, right? That also can happen. Ultimately, it's being balanced, right? I apply the force tangentially. I apply the force tangential to the surface. The area is like this. Area vector will go like that, but the force is like this, right? So this is known as shearing stress. What is the formula for this? This is the F tangential, right? F tangential, and this is the area A of the surface A, right? So F, the shearing stress is also given by the same formula, Ft by A. Here this is Fn by A. Here this is Ft by A, because it's normal to the area. Here it's tangential to the area, right? And because of the stress, what can the shape become? It can become something like this. In fact, I'll draw it here itself. It can become something like this, right? Your block might change shape to something like this, right? This is called as tangential stress or shearing stress. Coming to the third stress called bulk stress. What do you mean by bulk stress? So, for example, in a beaker, if I put some object, it is experiencing force from all the sides, right? Force from all the sides outside. So, this force, if I take this force on this part, the force acting is F, the unit area is A. So, here bulk stress is simply F by A. In fact, it is usually the pressure. Usually it is the pressure itself in the liquid, right? Because when you place the body inside the liquid, it is pressure which is actually compressing the liquid, right? F by A is basically the pressure. So you can replace that with pressure. Here also nothing wrong in saying that this is also a pressure, but usually it's more convenient to use it in bulk stress, right? We usually use it more often for bulk stress. For longitudinal stress problems, usually they'll give you the cross section of the wire, they'll give you the force or the tension which acts on the wire, and then you'll use this formula. But for bulk stress problems, usually you'll get something like a body is put in a beaker at a height h, at a depth h below the surface. So there you will not calculate F by A, you'll simply calculate the pressure at a depth h below the surface and use that in the bulk stress formula, right? So this was your stresses, these were your stresses. Let's look at strains. What do you mean by strains? Strain. The effect of stress on the body is called strain. So you are applying some stress on the body, because of that it will undergo some change of shape, right? That change of shape is called strain. It is basically change by original. It is usually change by original. That means if I'm talking about length, if the original length was L, I applied some force, the length became L minus delta L. That means actually the change was delta L, right? The change was delta L. Here it will become L minus delta L. If I pull it, it will become L plus delta L, right? But let your delta L be the change. So delta L by original length was L. Delta L by L is your strain. So I just explained you what longitudinal strain is. So longitudinal strain, it's nothing but delta L by L, change in length of the wire by original length of the wire, right? Very simple to understand. The second is what is known as shearing stress. Remember, shearing stress is very simple again. It is just this angle. Right? This angle that you see here, tan of this theta, like tan theta of this, and because it will usually be very small, because materials are not readily elastic, right? Materials are highly elastic, not readily elastic. It's very difficult to change the shape, right? It's very difficult to change the shape. So usually theta will be very small, so I can usually approximate tan theta to theta. This theta itself is the shearing stress, right? So if you know the height here, if you know the height of this, and if you know the delta x by which it got changed, so delta x by h is usually your tan theta, which is approximately theta, right? And that itself will be your shearing strain. Sorry, this is not stress. This is shearing strain, right? It's very simple. That's all. The third one is your bulk strain. So what will bulk strain be? Come back to this example. In bulk strain, what happens is there is pressure from all sides, like there are forces acting from all sides. So what it will do is it will usually compress the liquid, right? Compress the body, right? It will usually compress the body. So the bulk strain is change by original. What will change here? The volume of the body will change. So delta V be the volume change, right? And what will original volume be? Let that be V, right? Let that be V. So bulk strain is nothing but delta V by V. and usually it's taken with a negative sign because for such cases volume is always decreasing, right? It can never increase because there is no force from inside to outside which will actually increase. If that happens, if there is a force, if there is pressure from inside which increases the volume, then you'll use delta V by V. But usually we don't experience such cases. Usually it's most of the problems are like this, like it's put under water and pressure is acting from outside, then it will actually decrease the volume, right? It will always decrease. So that's why to keep the strain value will always be positive, right? To keep that constant, I'll use delta V by V with a negative sign usually. So with this, if I need the magnitude of strain, like usually I just need the magnitude. For that, I'll put the sign. So if your delta L is also decreasing here, and if I need the magnitude of the strain, if I need the magnitude of longitudinal strain, I'll just put a minus sign here, right? I'll put a minus sign, minus delta L, so that I actually need what is the change, what is the magnitude of the strain, right? So that is what I usually care about. So with this stress and strain basic discussion is done. Let's move into understanding the stress strain curve from where we'll understand what Hooke's law is. So let's proceed. So let's quickly understand what the stress strain curve is. So this is your stress on y-axis and your strain is on x-axis. You know what stress is? Force per area, right? Which is responsible for causing the change in shape, and strain is something which tells you how much the shape has changed, right? So this is stress versus strain curve. So how it goes is when initially 0, 0. That means there is no strain, no stress, the body is happily at rest. When you start increasing the stress, the strain also increases linearly, like this in this region OP as you see is linear, right? So in this region, stress is directly proportional to strain. In this region, stress is directly proportional to strain. This is called as Hooke's law. Hooke's law is nothing different. It is just this, that in this region OP, in the linear region OP, stress will be directly proportional to strain, right? So I'm telling you, I'm explaining this curve in a very, very short manner, right? There are few more points here, a couple of more points here, which are not really important from the exam point of view, but for understanding they're really, really good. So what happens here is until OP, it will be linear. After PE, this E is called as the elastic limit. Here what happens is, until this, if your strain is such that it is sigma E, so sigma is the stress, sigma is the stress here. So if you keep applying the force until the elastic limit, the body can come back to shape, right? But the only difference is in the region OP, the relation between stress and strain is linear, and in the region PE, the relation is non-linear. But if my stress is until sigma E, and if I remove that stress, it will come back to its original shape, like all the strain will be gone, right? But beyond sigma E, if I increase my stress beyond sigma E, then there will be some permanent deformations in the body, and if I keep increasing it, after a certain point it will reach a fracture point where the body will break, right? That happens. So there are a couple of more important points here, like not very, very important, but important from understanding point of view. So for us, the numericals that we look into will only be for this region, right? We won't be touching PE for numericals, and after that we're not even concerned. Like for PE also, the understanding is, okay, until I start increasing the force on this body, right? I start increasing the force. F by A is my stress, right? Until that stress reaches elastic limit, if I remove it, the body will come back to shape. But if I increase it more than elastic limit, then there will be permanent deformations formed in the body. And if I keep increasing it further, it will reach some fracture point, right? But in the region OP, it's linear. The relation between stress and strain is linear. This is called as Hooke's law, right? So from Hooke's law, we'll understand what is basically modulus of elasticity. So modulus of elasticity is nothing but very, very simple. Take Hooke's law. Stress is directly proportional to strain. So there will be some constant K which will relate stress and strain. Constant K. This constant K is basically stress by strain. It's stress by strain. This constant K itself is the modulus of elasticity, right? It's modulus of elasticity. So as you guys already know, there are three cases. There are three cases of stresses we have discussed. There are three cases of strain that we have discussed. So we have to discuss three cases of modulus also, right? The first modulus is called Young's modulus. Young's modulus. So Young's modulus, Y, is nothing but longitudinal stress by longitudinal strain. So come back to that case where you had a rod like this, right? If I applied some force F, the area of cross section was A, the original length was delta was L, but finally the final length LF was some L plus delta L, where the change is delta L. So change was delta L. So Young's modulus is longitudinal stress. Longitudinal stress is simply F by A, right? And longitudinal strain is nothing but delta L by L. We already know this, we have discussed. So the formula for Young's modulus is F by A into L by delta L. And trust me, repeatedly, whenever they ask a question about Young's modulus and anything else, it's only using this formula, right? I don't know why it's so difficult to understand this and solve most of the problems, right? So that's about Young's modulus. Coming to what do you say, shearing modulus, which is basically your eta, right? So it's how it goes is eta is represented by longitudinal what do you say, shearing stress. What was shearing stress? Shearing stress was your Ft by A. So in that body, if you remember, this was your theta, right? Theta. So theta was the strain. So strain comes in the denominator. So eta is something by theta. And what is this something? This is the F tangential, Ft force, right? Ft force. And the area of the cross section of the surface was A, right? So F by A. So eta is nothing but F by A theta. And that's all that you have to use in the problems. It's pretty simple, right? Coming to bulk modulus. Right. Bulk modulus again is very simple. B, it's denoted by B usually, right? It is bulk stress. What was your bulk stress? I told you, usually when the body is kept inside and it is experiencing some force from all side, pressure is usually your F by A, right? Pressure is usually your F by A. Pressure is usually your stress. So pressure divided by what was the longitudinal, volumetric strain or the bulk strain that we discussed? Delta V by V with a negative sign, right? So it is minus delta V by V here that you'll put. It's the same concept that you're using to derive all three. And it's very simple, right? And why am I putting a negative sign? Because I have to keep this positive. Pressure is positive. Delta V is usually negative because volume decreases. To compensate for that, I'm using a negative sign, right? That's all. That's all about the moduli that you have to know. In fact, so they can ask you a lot of problems around this. So sometimes they'll take a gas, right? And they'll put the gas under some pressure, and the gas also will behave in an elastic manner, right? So for that they'll ask you what is the modulus of this process, right? It's essentially using the same concept. Just try understanding this and solve those 5 to 6 models that I told you in the beginning, right? Which are actually important for you to understand this chapter. I can't really teach you all of that right now because this is a short session, and in this short session the concept is only this much, right? So you have to solve those models to understand how to do different problems which will use the same concept, the same formulas, right? It will be very simple. So with this, we're done with our discussion on moduli. So let's very quickly look into understanding what Poisson's ratio is. Poisson's ratio. It's pretty simple. What happens is when you have an object like this, right, a body like this, if I subject it to some force F, so I'm taking account of its length increasing, right? So I'm saying that okay, the length is increasing to this much. But actually, is it possible? Is it possible for the body to be this thick and increase its length? No, right? Because the volume will actually increase. If you're increasing the length, if this is a cylinder, then pi r square h, where your h was the height, r was the radius. In fact, let that be L. So pi r square L is the volume. This has to be constant, right? If I'm increasing my length to L plus delta L, that means the volume is increasing. But how can I increase the volume? The volume is actually not increasing. So what's happening here is the radius is decreasing. So when it's increasing like this, the radius is slightly decreasing, and Poisson's ratio accounts for that. So I will say there are two kinds of strains. One is the strain which is caused due to increase in length. The other is caused due to decrease in the radius, right? There is a decrease in the radius. If your length increases, then radius will decrease, right? So sigma, which is your Poisson's ratio, is this strain delta L by L divided by this strain delta R by R, right? It's simply delta L into R divided by minus delta R into L. Now why is this minus sign there? If your L increases, then R will decrease. If your L decreases, then R will increase, right? It will make sure, this minus sign will make sure that sigma is always positive. The theoretical value of sigma is always between, so the theoretical value is between -1 to +12, but practically what we see, the practical value is always between 0 to +12, right? It is just random data that you're supposed to remember from the exam point of view. But ultimately, if any problem is asked about Poisson's ratio, it's usually this concept, right? So with this done, we'll only look into the last part of the chapter, which is potential energy stored in a stretched wire. In fact, I won't even derive this. I'll just tell you what the formula is. I'll tell you what the terms in the formula are. So it's very, very simple. Again, if I just take it, if I take this wire, it's a wire with some area of cross section A, right? Length L. If I increase this length to some L plus delta L, the change in length is delta L. The strain here is obviously delta L by L. If I do this with a force F, like a normal force F, right? This is a normal force, remember. Area of cross section is A. Area of cross section is A from on both sides. Then your stress is F by A, right? So the energy that's stored in this stretched wire, the energy stored, let that be capital U. Energy stored per volume of the wire. The volume of the wire is obviously the volume of a cylinder, right? So volume of a wire, this quantity is half into stress into strain, and the derivation is very, very simple, right? So read that from the textbook. It is just that the restoration force keeps changing with distance, right? It's just like a spring which has a constant K, right? So it's sorry, not a resistor, a spring. So a spring which has a constant K, right? So if I stretch it with some X, half Kx square, right? How is this derived? It applies a variable Kx force which is integrated over a distance 0 to X, right? That is the work done. And that is the energy stored in the spring. It is something like that. It's very, very similar, right? So just read the derivation yourself. I'll tell you, I'll just give you a hint. Your K will be some YA by L, right? And X square will be simply your increase in the length, which is delta X. So you just put that, read the derivation yourself, and you'll get to this. So remember, this is small u. I'm just telling you what the formula is, right? So small u. Remember, don't write energy stored in spring, energy stored in wire. Don't write energy stored is half into stress into strain. So your half into stress is basically F by A, and strain is basically delta L by L whole square. Sorry, delta L by L, right? And in fact, when you use this K is equal to YA by L in half Kx square, right? Where you put X equal to delta, you'll get this formula. But this is slightly wrong. You're not supposed to write energy stored is this. You're supposed to write energy stored per volume. Energy stored per volume is this, right? So if you want the energy that's actually stored, you're supposed to multiply this quantity into the volume of the wire, right? Which is your obviously pi r square L. Keep taking into account that your delta L is very small. Pi into r square into L is the volume. You're supposed to multiply this quantity to this, and then you can say that the energy stored is half into stress into strain into pi r square into L, which is the volume, right? So with this, I would like to conclude the chapter. The concepts, as you can see, are very, very simple, right? And in fact, the problems also will just be playing around with these concepts, right? You just have to do some 5 to 6 or to be in a much more safe position, some 10 different models of this problem, and then you're sorted. You'll actually understand the feel as to how all of this works. And it's very, very simple. As I've already told you, this chapter is basically free marks. So don't miss out on this. Prepare well. I hope you enjoyed the session. Thanks for watching.